Hi, this is the lab report for the fourth lab, macroscopic view of DC and RC circuits. In this lab, we'll use a virtual lab to investigate the role of ohmic resistors and capacitors. And also we'll learn to use the ammeters and voltmeters and learn how the resistors in parallel and series work. Also, we'll calculate the time constant, which is the RC value of the RC circuit, and compare the calculated value with our expected value of RC. The physical principles that I used in this lab are energy conservation, which is also called the loop rule, and current conservation, which is also called the node rule. I'll also use the Ohm's law, which is R equals to delta V over I, and also delta V equals to Q over C, in which C is the capacitance of the capacitor. In the next section of the lab, we focus on the charge conservation and energy conservation in series circuits. As shown in the graph on the right, the two resistors are placed in series, and I used the voltmeter to measure the voltage difference between different points from A to H. I always put the red lid of the voltmeter at the positive side and the black one at the negative side, so that the delta V adds up to 0. Also, the ammeter is 0.02 amperes, which shows the current in the circuit. Then I use my measurements of the potential difference between different points to create this graph of potential versus position. When I attach the voltmeter to the circuit, the ammeter's reading doesn't change because the voltmeter has a really large resistance inside itself, so it just acts like a shortcut in the circuit, and the current won't go through the voltmeter. However, if I put an ammeter in parallel with the 100 ohm resistor, the readings of the ammeter changes to 0.06 amperes.
The ammeter has a really small resistance inside, so ideally it can just act like a wire, so when it's in parallel with the resistor, the current just goes through the ammeter instead of the resistor.
So in this way, the ammeter is 0.06, which is the value of 3 over 47. Using the measurements of potential difference in the previous parts, I can calculate the resistance of the two resistors and the resistance of the wire and the ammeter. Here I found that the calculated value that I got are similar to the expected values. In the next section of the lab, I focus on the RC circuits. First of all, I can connect the batteries to a 10 ohm bulb and a capacitor of capacitance, which has a capacitance of 0.2 farads in series. The bulb in the circuit started bright and then got dimmer and dimmer. The current was about 0.87 at the very beginning and decreased to 0 when the capacitor was fully charged. And then I disconnected the battery and connect the capacitor directly to the 10 ohm bulb. The bulb was bright for a short time and went dim again. The current in the circuit starts from around 0.87 to 0 LS. So the time used to charge a capacitor in series with a 10 ohm bulb is around 21.48 seconds. Well, when I change the 10 ohm bulb to a 20 ohm bulb, the charging time is around 41.02 seconds. Based on the behavior of the capacitor, I'm going to calculate the RC value, which is also called the time constant of the capacitor. If I only connect the capacitor with a resistor, we can tell from the loop rule that delta V capacitor plus delta V resistor equals to 0. And since delta V capacitor equals to Q over C, we can tell that Q over C minus IR equals to 0. And then by replacing I with negative dQ over dt, we can get that dQ over dt equals to negative Q over RC. And since the potential difference across the capacitor is proportional to the Q value, we can get that delta V equals to delta V naught times e to the negative t over RC by taking the integral of both sides. And then if we take the natural logarithm of both sides, we can get ln delta V over delta V naught equals to negative t over RC. And here delta V naught is the potential difference across the capacitor when t equals to 0. So using the CCK, I record 20 sets of delta V and t, and then I plot the graph of ln delta V over delta V naught versus t. So as shown on the graph, and the slope of the line is negative 0.167, and from the function that we got previously, RC equals to 1 over 0.167, which is similar, which is close enough to 6 seconds. And our expected RC value is equals to R times C, which is 30 ohms times 0.2 farad, which is also equals to 6 seconds. Here I have 2 extra questions to answer. First one is, what if I was doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? And in real life, the resistance inside the ammeter is bigger than 0. So the current in section 1 could be smaller when the ammeter is in parallel with the resistors. And the second question is that what if I was doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? I think the real battery will have a resistance inside of itself, which will definitely slow down the charging process. And the capacitor was charged really fast in the CCK model, but capacitors in real life will be charged more slowly. And moreover, the capacitors may never be fully charged in real life due to the resistance in the batteries and the wires.
In conclusion, in this lab, I've learned how ammeters and voltmeters work, how capacitors are charged, and how they work as a power source when they're connected with a light bulb. And I also my calculated time constant in the RC circuit is close enough to the expected value. And thank you for listening.